Hello, welcome to this video. So in this video we're going to be exploring the magical world of the number e, also known as Euler's constant. And I thought it was important to do a video on e because e is one of those amazing numbers that comes up so much in mathematics. You can use e for kind of like population growth, where there isn't much limit in supply and resources. E plays a fundamental role in solving linear differential equations. E is a very important constant within Schrodinger's equation. E plays a sterling role in the Euler identity. So E is super important within physics and has many applications. But sadly, although pi is very well known outside of the mathematical community, E isn't so much. So this is a promotional video almost for E, and we'll be exploring what E is geometrically, how to geometrically think about E, much like we might explore how to think about pi geometrically when first introducing pi, but then we'll be going on to looking at ways to approximate a numerical value for E using quite novel methods, I think, including talking about compound interest. So E might have more to do with your savings accounts than you might at first guess. And then we'll be finishing up with a bit of complex analysis at the end. So without further ado, let's fly like a butterfly through the magical lands of E. Now we've introduced some applications of E, let's look at what E is geometrically. We're going to start with geometry. So we're going to start with how curves look and think about the derivative of curves. Now to do this and see how it relates to E, imagine a function y equals a to the power of x, where a is some positive constant. Well, if x is positive and x increases, then our function y equals a to the x will increase. Also, the derivative of y equals a to the x will also increase. And we might wonder, is there a special constant a for which the derivative of y will match the value of y? For all values of x we might give the function. And it turns out, yes, there is a special constant that a can take, such that this is true, and that constant is called e. So e is a constant such that if y equals e to the x, then dy by dx will always equal y. Now you might wonder, if you haven't seen E much before, where would you use this, or where would this relationship come up? Well, it turns out that the idea of the derivative being proportional to the output of our functions, in this case y, happens a fair bit in nature. So like, imagine it's a snowy morning and you wake up and you pour yourself a mug of tea. Initially that tea is really hot, so it's at a large temperature difference to the surroundings, and therefore is losing heat quite quickly, so its temperature is dropping quite quickly initially. So for a high temperature, so for a high capital T, we have a high rate of change of T. Whereas as the mug gets cooled, so as T drops, as the temperature of the mug drops, it gets closer to the temperature of the surrounding environment, and therefore it loses heat more slowly. So as the temperature T diminishes, the rate of change of the temperature also diminishes. And it turns out, for that kind of system, the temperature is proportional to the rate at which the temperature drops, and so we end up with some kind of exponential curve for the temperature of tea or coffee. So, you know, this number e is useful for very well for things in daily life as well as more abstract purposes. So that's the main way to think about what e is. Now, because acting a first derivative on e to the x doesn't change e to the x, it follows that if we have an nth order derivative on e to the x, we will always get back e to the x no matter what integer value n takes. Now in this video, we're not going to be worrying about taking fractional derivatives, so we're not doing fractals or anything like that. So n is always an integer, and due to how we've defined y equals e to the x, it then follows that the nth order derivative of y will always give us back y. So you can think of y equals e to the x as the magical kind of function for which kind of like the derivative operator has no effect on it. No matter how many times we apply the derivative operator to e to the x, we always get back e to the x. It's like some of those Dark Souls bosses, which no matter how many times you try to hit them with something that they are resistant to, their health bar never seems to change. So, e to the x is a function that is resistant, if you like, to derivative operators. So that's the most common way to think about e to the x. It's worth saying a bit of notation that is quite helpful if we're considering the nth order derivative, particularly if we're thinking of approximating e as a series of terms for which each term will have a different nth order derivative. A very useful notation for the nth order derivative is to put n in brackets and put it above the y, so have the brackets with n inside as a superscript. Now we put brackets there to emphasize that we mean the nth derivative of y. We don't mean we're applying the function y n times to our input x. So the brackets indicate that we're taking the derivative, some derivative of y. And we use that notation when we look at a Taylor series to get a good approximation, a numerical approximation for e. But just to finish up on ways to think about e geometrically, we can use the fundamental theorem of calculus, that the integral of the first derivative of y with respect to x integrated over x will give us back y plus some constant of integration. To evaluate the integral of y equals e to the x, and when you do that, you can show that the area of this shaded orange region, I don't know why I said purple, the shaded orange region has an area of 1. And I leave that as a kind of like fun exercise to the viewer. So that's another geometrical way to think about e to the x. So e is the number such that e to the x forms this area bounded with the y-axis and a kind of curve, and the orange area will equal 1 for our special constant, or Euler constant e. So those are different geometrical ways to think about e. But just as, when you do kind of like circular geometry, you might be introduced to pi in terms of, pi is the ratio of the circumference of a circle to its diameter. you quickly need to actually have a numerical value applied to use it in calculations. The same kind of thing is true for E. So now we've got a geometrical understanding of what E is. Let's look at one way of getting a numerical approximation for E based upon this geometric understanding of Euler's constant. Having introduced what is geometrically, let's look at a first method for getting an approximation to the numerical value of E. And as with the majority of kind of approximations within physics and many in mathematics, we have to thank for this a series developed by Taylor. Now, in kind of mathematics, there's two different types of sequences. The Maclaurin series, which I believe was developed by a Scottish mathematician, and we also have the Taylor series. But physicists commonly just call anything that looks like a Taylor series a Taylor series. So for the purpose of this video, I'll be talking about Taylor series, although I cannot quite recall if, strictly speaking, it's a Taylor or Maclaurin series. You know, the important thing for this video is a series, but I feel like Maclaurin deserves a mention, definitely. Now, a Taylor series is a way of taking something that isn't a polynomial, so potentially functions like e to the x, or other functions which are smooth and kind of infinitely differentiable around a particular point, and, you know, rewriting that function as a polynomial. Now, if you want to rewrite that function exactly, you'll typically have a polynomial with an infinite number of terms, but providing, you know, that function is smooth and doesn't diverge at the point you're trying to expand the function around through the Taylor series, you know, the Taylor series won't usually be divergent, so you'll only need the first few terms to get a good approximation, a good polynomial approximation for your function. And, you know, physicists being physicists, we typically expand around the point where the input of the function is 0. You don't have to do that, but just because of the way we design our equations, we're typically interested in how things vary around the input equaling 0, because we calibrate our devices such that that is physically significant, such as, you know, you might wonder, how does a mass on a spring move? And you'll probably consider, how does it move at the present time, and we quickly take the present time t to be 0. So you're looking at the motion under which the input t is 0. So, you know, generally we want to vary our function around an input of 0. But anyway, the Taylor series has this kind of form. Now, as I say, strictly speaking, the Taylor series has an infinite number of terms, making the series even longer than Taylor's rather luxurious wig. And n therefore goes from 0 to infinity and up in integer steps. Now we can use this Taylor series expression to get a Taylor series expression for our function y equals e to the x. Now remember, the special property of e to the x is that no matter how many times we act a derivative operator on it, we get back e to the x. So in other words, we can replace the nth order derivative in our Taylor series with just y. And so replacing the nth order derivative of y with y, we get that for the function y equals e to the x, the Taylor series for y should be the sum over n from n0 to infinity of y of 0 over n factorial x to the n. And one of the nice things with Taylor series in terms of e to the x is that thanks to the property of e to the x, we don't even have to do any differentiation really to get the Taylor series for e to the x, which makes me very happy, because I don't like differentiating things an infinite number of times personally. Now, y of 0 is going to be a constant, because y of x is a variable, but if we give x is equal to some constant, say 0, we're going to get out another constant. So y of 0 is a constant, so we can pull that out of our summation sign, i.e. it's independent of n, and we get this expression. Now we can use the fact that y of 0 is by definition e to the 0, which is just 1, and that means that our Taylor series for e to the x actually looks really neat indeed. Now we want to find a numerical approximation for e, and clearly we're going to get e to the x equaling e when x is 1. And we can use the property that 1 to the n is going to be 1 for all real numbers n. Now it's worth saying if n was a complex number, this wouldn't work. 1 to the n isn't necessarily equal to 1 if n is complex, but for a real number n, 1 to the n will equal 1. And so our Taylor series expansion for e, just the number e, is the sum over n of 1 over n factorial. Now n factorial gets dramatically bigger as n increases. Therefore 1 over n factorial gets dramatically smaller as n increases. So we only need the first few terms to get a good approximation for e, because the latter terms are going to be insignificant. They're going to be small compared to our first few terms. So if we look at the first 5 terms, we can kind of see this pattern. Now, to get a kind of numerical estimation for e, I'm just going to use our first 4 terms, because 1 over 24 will have a negligible effect on our approximation for e. So e will be about 1 plus 1 plus a half plus a sixth, which is about equal to 2 plus a half plus something that's close to a fifth. So e is about 2 plus 0.5 plus 0.2, so e is about 2.7. So the Taylor series is so nice for e. Actually, we can get an estimate for e without even using a calculator, which I like almost as much as I like not having to differentiate things an infinite number of times. So that's one way to get an approximation for e. We're now going to have a look at another way of approximating e, where we're going to be introduced to the Bernoulli family. A very, very important family within the world of mathematics. We've had a look at using the Taylor series to estimate a value for e. Now let's move on to the Bernoulli family. So the Bernoulli family were a family of mathematicians, and I don't know whether it was genetic or whether it was kind of hereditary, much like many chefs have close family members which are also chefs. But the Bernoulli family contained a highly unusual amount of mathematical geniuses, for want of a better term. And the Bernoulli family were kind of like the mathematicians of the day during their time. So one Bernoulli, for example, was one of the founders, kind of like the main founder of the calculus of variations, which is the piece of maths used in Hamilton's principle of least action, arguably the most general principle within physics. You can apply it to classical systems like mass oscillating on a spring. You can apply it to much more abstract systems such as those involving black holes and general relativity. And ultimately, the Einstein field equations can be written in terms of Hamilton's principle of least action. So, the calculus of variations has given physics so much, and arguably from what we can see a fairly fundamental principle. Jacob Bernouli was another of the Bernoullis, and Jacob Bernoulli started to be interested in something called compound interest, if you pardon the pun. Now, compound interest is where you get interest on top of previous interest. So, with a compound interest, the amount of interest you get, say, in a savings account, is based upon not just the original amount put into the savings account, but the total amount there, including previous interest, before the new interest is taken. So with compound interest, the new interest is a percentage of the total amount in an account, and that includes the amount that the account has grown thanks to previous interests. And when you study compound interest, and it's well worth studying because you can save up a lot of money by putting money into a savings account and then waiting many years. And through compound interest, you can build up quite a bit of savings. So, it's potentially really worth studying. But compound interest also, it turns out, gives a way to calculate E, and we'll look at that in a sec. So here's our formula for compound interest, and for those who are interested, here are what the symbols mean within the expression. Now, I'm not going to go through what each one means in key detail. The key thing is that A is the total kind of like amount in the account, if you like, and N is the number of times the compound interest is applied within a kind of a unit time period. Now, what Jacob Bernoulli was interested in was what happens in the limit where compound interest is applied continuously. So what happens, or what do you get for the total amount in your account as n goes to infinity? Because if compound interest is applied continually, then within any finite amount of time, you've essentially had the compound interest applied an infinite number of times. So we're considering what A is in the case where n approaches infinity. So that's what Jacob Bernoulli was thinking about. And so the kind of limits he ended up considering were of the form, the limit as n goes to infinity of 1 plus 1 over n all to the power n. Now I'm giving that limit the symbol x. It turns out that x is actually equal to e, in that this limit we've got as n goes to infinity is another way you can define the Euler constant e. It's another way of expressing it. And I'll discuss why taking the limit as n goes to infinity leads to an expression which allows us to calculate e at the end of this part of the video once we've used this limit to calculate e. Now, I'm showing this way of getting the numerical value for e, partly because I know many mathematicians enjoy looking at limits, and I think it's a quite cool limit to consider, you know. It's not a kind of standard limit like the limit to a geometric series, it's quite a unique limit. So worth going over perhaps in a bit of detail. So how would we calculate this limit and get a finite solution for it? So how can we think about this limit in a way that this kind of expression will converge as n goes to infinity? Well, as n goes to infinity, 1 over n is going to be quite small. So we're thinking of calculating 1 plus something that is much smaller than 1 all to the power n. And those of you who have seen the binomial series before will know that this is heavily indicating we should use a binomial series. So the binomial theorem, when applied to our expression in brackets raised to the power n, looks something like this. Now, I'm not going to go into detail about how the bit in brackets to the power n reduces to the sum of n factorial over k factorial n minus k factorial into the k. And that's because going into the detail would kind of require a video on binomial series, and I don't want to go too far off track. However, there are many great resources, and all I've done is apply the binomial theorem, so if you are unsure with how we've gone from x equaling a limit of something to the power n to x equaling the limit of a sum of terms, I would recommend checking out a PDF or something on binomial series, and then you can apply it directly here. Now, the question we have, if you want to work out what x is you know, what are the first few terms of this binomial series? And, you know, because n is getting quite big, and therefore 1 over n is going to get much less than 1 as n approaches infinity, this series should converge, so we'll only need the first few terms to get an approximate value for our Euler constant e, which here has a symbol x. So let's consider the first few terms of this sum. So here I wrote the first 4 terms. Now, as an example of how we get this approximation for x, where I'm considering these first 4 terms, let's look at the third term in this approximation. So n lots of n minus 1 over 2n squared. So how do I get that using our sum? Well, our sum is from k equals 0 to n, where k is going up in integer steps. So the third term will correspond to k equals 2. So what is n factorial over k factorial times n minus k factorial times n to the k when k is 2? Well, n factorial over n minus k factorial would be n factorial over n minus 2 factorial, which would leave us with n lots of n minus 1. So that's where the n times n minus 1 comes from in our third term. And the 2n squared in the denominator of our third term comes from the fact that when k is 2, k factorial times n to the k is going to be 2 times n squared. So that's how I got the third term, and you can do a similar thing, although it's a little bit more complex, to get the fourth term of our approximation for x, or our Euler constant. Now usually we're trying to simplify things, but having our approximation for x, where we have things factorised and therefore in their simpler form, isn't really helping us move forwards. So let's try expanding the brackets. And once we've expanded them, we can spot that actually expanding our brackets is giving us something very beneficial. So, for example, if we look at our third term again, so when we've expanded our brackets, it's written as n squared minus n over 2n squared. The n squared over 2n squared, our n squares will cancel out, and we'll have a term that is independent of n, whereas our minus n over 2n squared will give us a term that does depend on n, which will vanish, so go to 0 as n goes to infinity. Applying that logic to the fourth term, we get this, and using what I said, well, clearly 1 over 2n is going to go to 0 as n goes to infinity, and in fact 1 over 3n squared is going to go to 0 even faster than 1 over 2n as n goes to infinity, because 1 over n squared drops off much more quickly than 1 over n, if n is quite a big number. So what that means is, from our first four terms of our binomial approximation for the Euler constant, we get some fractions from our two latter terms, and those fractions help us get a fairly accurate answer for E. So E, or x, should be about 1 plus 1 plus a half plus 6. And that's exactly the same terms we got before when we were trying to get an approximation for the Euler constant. So the Euler constant is going to be, like before, approximated to about 2.7. Now, to fulfill the promise about what I said about justifying why x has something to do with our Euler constant E, before we began trying to find a numerical approximation for E using the binomial series, well, we began with taking the limit as the compound interest becomes continuous. Now, the compound interest increases as the amount in the account increases. So for compound interest, dy by dx will increase as y increases, and we might expect dy by dx to be in fact proportional to y. So we would expect, based on the fact that compound interest is interest essentially on top of interest, we would expect that the rate at which interest increases is going to be proportional to the amount in the account. So we have the kind of proportionality between the derivative and y to give us kind of like exponential growth for the amount of money in the account, and that's further comes into fulfillment in the limit where n goes to infinity, because in that limit our growth in our kind of amount in the account becomes continuous. So we get a continuous graph for which the rate of change is proportional to the amount of money in the account or proportional to y. And so, based on our geometric intuition for what e to the x is, we would expect the limit as n goes to infinity of a compound interest formula to become exponential-like, and thus it makes sense that e would appear or would be related to our limit. And you can do more rigorous proofs if you like, but I think that's a nice way to think about it. So we now talked about a couple of ways of estimating a value for e. Let's move on to seeing how you can use e, or how e arises in places where you really might not think you would see it. And that will give us a deeper and more abstract intuition for what the constant e is geometrically representing. Having seen lots of stuff with e and a couple of ways of estimating its numerical value, you might feel like we've talked fairly concretely about what e is. And that is, you might think that e will only come up when we're considering cases where dy by dx is proportional to y. However, it turns out that this isn't really the case. And this is because e, in many ways, has a kind of resemblance to the nature of pi. So when you first learn about pi, you're usually introduced to pi explicitly through circles. And you kind of begin to relate, almost subconsciously, pi to circles. But then, as you go forward with maths, you might start looking at the area of an ellipse, or something that isn't quite a circle, and pi appears there. And then, if you go much further, you will start to see pi pop up in all sorts of places which seemingly have nothing to do with circles. Like if you want to find the area under a Gaussian curve, and a Gaussian curve seemingly has much more to do with Euler's constant than it does to do with circles. But if you want to find the area under a Gaussian curve, it turns out that the area is proportional to the square root of pi. So pi appears even where there doesn't seem to be anything to do with circles. And eventually you start thinking about pi as being a symbol to indicate that there is some symmetry if we are using a Euclidean notion of distance. So wherever you're dealing with a shape or a function that is symmetrical, and you're defining symmetry using the Euclidean notion of distance, so using Pythagoras' theorem, pi will appear somewhere. That shape, that function will be related in some fundamental way to pi. And similarly, although we start with thinking about e geometrically as being specifically related to cases where y is proportional to dy by dx, even if that condition doesn't hold, it turns out there are uses for e. So e turns out to be useful whenever you have a function like y equals a to the x, even if that function is particularly peculiar. So even if a isn't a constant, it turns out that e will be useful. So as an example of this, let's consider the function y equals x to the x. So this is not an exponential function. And it's not an exponential function, you could say, because it doesn't have the form of y equals a to the x where a is a constant, but also the derivative of y with respect to x is not proportional to y. So this is not an exponential curve. However, e still plays a fundamental role here. So let's take a question for example. Let's ask, when is the first derivative of our function y equals x to the x 0? Now, as I said, x to the x is not an exponential function, and yet, if you differentiate x to the x, you can work out that the derivative of x to the x is 0 when x is equal to 1 over e. So e has appeared even though y is not an exponential function. And this emphasises the point that if our function is anything like y equals a to the x, even when a isn't a constant, so even when we're not having an exponential function, still Euler's constant will play a starring role within some fundamental property of our function. And the stationary point or the turning point of our graph, so the point where dy by dx is 0, is very important, because, for example, if we're taking our function y equals x to the x, then our graph switches behaviour at our turning point. So for x less than 1 over e, the gradient of our graph is negative, whereas for x is larger than 1 over e, our gradient of our graph is positive. And also a nice cool thing about our function y equals x to the x is it creates interesting debates around limits as x approaches 0. Now it turns out, although 0 to the 0 is traditionally considered as undefined without further information, it turns out that the limit of x to the x as x approaches 0, but approaches 0 starting from a place that is bigger than 0, it turns out that that limit is well defined, and that limit is equal to 1. So, there are cool stuff regarding the limits of x to the x. But anyway, the thing I want to emphasise is that even though we don't have an exponential function, the Euler constant plays a starring role. Now, you can use A-level maths to work out that dy by dx is 0 when x equals 1 over e, but I'm not going to go through it here, but I would heavily encourage you to have a go playing with y equals x to the x, and I would recommend using logarithms and see if you can play around with it and prove that when x is 1 over e, the first derivative of y is 0. It's a cool kind of function to differentiate. But maybe I've just done too many functions. But anyway, we're close to the end of the video, so I would say if you've enjoyed it this far, I would recommend hitting the bell icon or subscribing to get more videos like this on the channel. This channel has lots of videos on maths and physics, and to give just a little bit more maths, we've seen that the Euler constant is actually a little bit more abstract than we might first thought about it, in that it plays a starring role in things quite different to exponential graphs. That's ramp up the weirdness of e, and let's consider introducing some complex numbers and do a tad, a twinkle, a tidbit. I do like playing with words, but anyway, a tidbit of complex analysis. Having seen a couple of ways of getting a numerical approximation for the value of e, And seeing that E has a broader role to play in mathematics than purely just exponential graphs, let's move on to the magic of E, where we're dealing with E raised to the power of some complex variable. Now, traditionally, we take a complex variable to have the symbol z, and z is defined as x plus iy. Now we can ask, is e to the z differentiable? And our intuition, as it is usually built from real functions, that is functions of real variables, would go, well, surely e to the z is differentiable. Surely, that's the whole thing with e. E is about differentiability, so surely e to the z should be differentiable. However, when we move to the realm of e to the z, where z is a complex variable or complex number, things become much more nuanced, is probably the right word. So we're going to begin by assuming that although z is a complex number, e to the z can be broken up like we would if z was some kind of like combination of real numbers or real variables. And we're fine to do that because when we look at rules for combining powers, if there is a common base between two terms, we extend those rules all the time in real analysis. For example, we define x to the 0 to be 1 based on extending the pattern of, lowering the power means dividing something by x, and that leads to the conclusion that x to the 0 should be x to the 1 over x, which is 1 lot of x over x, which is going to be 1. However, we can't use our intuition to directly work out what x to the 0 should be, because what does it mean to have 0 lots of x? So we extend the rules for powers all the time with real numbers, so it's fine to do it in the complex case as well. And doing it in the complex case, we see that e to the z is some real function e to the x, so a traditional exponential function, multiplied by some phase factor e to the iy. So this is kind of like almost like an exponential growth, but with a unit complex number allowing the phase, if you like, of this function to change. So, that's what e to the z breaks down into. And breaking it down into this is helpful because it emphasises that e to the z is the product of a real function and a function that exists in the complex plane. Now, when we're looking at differentiating e to the z, we have to think in what direction are we changing z? Now, if z was a real number, let's say z was x, then differentiating e to the x, there would be no ambiguity in what we mean by in what direction are we changing x. Because if x is a real number, then x doesn't have multiple parts, so there's only really one direction we can move in if we're changing e to the x, that is, we're shifting our input x along the real number line. However, if we're considering differentiating e to the z, well, z has a real part and an imaginary part. So when we're changing z by an infinitesimal amount to work out the derivative, do we mean we're changing z an infinitesimal amount along the real axis? So are we changing x by an infinitesimal amount? Or are we changing z an infinitesimal amount by changing the imaginary part of z, so changing y an infinitesimal amount? So, which of these are changing infinitesimally, x or y? So there's a bit of ambiguity when we're saying we're going to differentiate e to the z. So let's have a look at what happens when we differentiate e to the z by changing x, and then see what happens if we differentiate e to the z by changing y. So if we're differentiating a complex variable, I'm going to use partial derivatives rather than ordinary derivatives, because we're changing our input z along a particular direction, so we use partial derivatives in this case. So the partial derivative of e to the z with respect to x will be just the partial derivative of e to the x with respect to x multiplied by e to the iy, and using the founding principle we really began with for defining e, that the derivative of e to the x with respect to x is just e to the x, we get that the result of our differentiation for e to the z should be e to the x times e to the iy, which is by definition e to the z. So if we're differentiating e to the z by changing z infinitesimally along the real number line, we do get back e to the z, much like we would if z was a real variable. But if we differentiate e to the z along the imaginary axis, so we change y infinitesimally, we do get something different to e to the z. We get I times e to the z, and you can verify that straightforwardly using a change of variable and then the chain rule. So we're getting two different answers to our derivative of e to the z based on which direction we're varying our complex variable z. So whether we're varying z along the real number line or the imaginary number line. And you know, clearly these two results are not equal to each other, simply because 1 does not equal I. You know, 1 does not equal the square root of -1. So what that means is that there isn't enough context to make any sense of talking about the derivative of e to the z with respect to z, because we'll get different answers based upon whether we're varying z along the real number line or the imaginary number line. So f of z, if f of z is e to the z, does not have a well-defined first order derivative, in that we're getting different derivatives based on additional information, like in what direction we're varying z. So we can't make any sense of dez by dz. So in general, e to the z will not be differentiable. That is, if we're allowing z to be complex, e to the z cannot be differentiated. We can, you know, differentiate if we have further information, but we can't evaluate statements like the derivative of e to the z with respect to z. There just isn't enough information there. And I think that's really cool, because it's a kind of contrary to our expectations. So it turns out that e to the z is never differentiable. It's never analytic. If z is a complex number and, you know, retains both a real and imaginary component. Now you might wonder, where do you use this? Well, working with complex functions is very important in fields like quantum field theory. It does also appear in other places. If you start, you know, going very deeply into things like scattering theory, you will likely need to start using complex analysis. So worrying about differentiating and integrating complex functions. But, you know, although e to the z is existing on the complex plane, and therefore to properly visualise both the inputs and outputs, I would need 4 dimensions of space, 2 dimensions for each of the real, well, 2 dimensions, for the input and 2 dimensions for the output, because both the input and output are kind of 2-dimensional numbers. But I can't draw a 4-dimensional image. But we can, get a feeling for how e to the z isn't differentiable by using a kind of real analogue. So here I've sketched a function e to the z is equal to e to the x times e to the y. Now we can imagine replacing y with I times y, and we'll be getting our complex function to the z. So, or something, it's analogous if you like. As I say, it's not a perfect one-to-one mapping, but it's an analogy. But we can see here clearly that the graph kind of looks slanted and is varying differently along the y-axis compared to the x-axis. Now I wouldn't worry about the graph too much. It's mainly an analogy to show that, if we're dealing with kind of functions which, although taking a number that can be split into 2 distinct parts, we might well expect the differential of a function to depend upon the direction we take that derivative in. So, I think that's everything for this video. So we've talked a little bit about what is geometrically, how to use e in cases outside of the usual exponential growth examples. And we finished by looking at some more of the magic of e. I really hope that you got something out of this video. There'll be more maths videos coming up on this channel soon, and I'm wishing you a really good week ahead.